Okay, I'm going to discuss about second law of thermodynamics and the quantitative measure of irreversibility is given by entropy. That's what we are going to discuss. So, in terms of what we did in the class, we went a little bit backward. The general equation for the entropy change is entropy in minus entropy out, and then entropy is not conserved, so you have entropy generation equals to change in entropy of the system. If it was energy, it would be energy in minus energy out equals to change in energy of the system. Energy in and out could be due to a heat transfer, due to work transfer, and due to mass transfer. Okay, whereas for the entropy, it can be due to heat transfer and it can be due to mass transfer, and there is no entropy transfer due to work. So this is a big difference between um, entropy transfer. Okay, so based on that, you can write entropy balance equation for the closed system as well as for the open system. For the closed system, there is no transfer of mass, so you don't have the entropy transfer due to mass. The only thing you have is due to heat transfer. So that is why you have, this is the entropy transfer due to heat, and then you have entropy generation equals to change in entropy of the system. And in some of the, in the closed system, if it is adiabatic or if there is no heat transfer, if Q is zero, then or then this becomes entropy generation equals to change in entropy of adiabatic system. Okay, so if you want to find out entropy generation of the closed system, like you have this system and then you have surrounding here, the way to find is you consider both the system and surrounding as the whole universe, so that this here, this should be your isolated system. And in that case, if this is a boundary which include both the system and surrounding, then Q is 0, W is 0. So in that case, the entropy generation would be entropy change of the system plus entropy change of the surrounding. So whenever we are trying to find the entropy generation for the closed system, you have to consider the entropy change of the system as well as surrounding. This is the way to do it. This is the case when we consider as an isolated system or there is no heat transfer and it includes both the system and surrounding. The other case could be when it is reversible. When it is reversible, then entropy generation would be zero. So Sgen would be zero. Okay. So in that case, ds would be dq by t. Again, remember, you can't use this everywhere when it is internally reversible. So this equation can be used when the heat transfer is given and you have a temperature. So this is the key parameter here, and this equation can only be used when it is closed system and it is internally reversible. If it's not internally reversible, this S generation will not be equals to zero. Okay, so this equation can be written as this way, and like in thermal reservoir, the Q may be constant and temperature may be constant. So this is the most popular equation used if it is a thermal reservoir. If you know the Q and T is, if T is constant, then this is how you find the change in entropy. So one of the variables that you'll be asked to calculate is um, the change in entropy, and this equation is used when it is a reversible and we know the value of Q and temperature is given. This is how you use it. Okay, and so from here in the closed system, the two important things, one is knowing how to calculate change in entropy when it is a reversible, internally reversible, and also how to calculate entropy generation. Okay, so those are the two things which you need to focus on when it comes to closed system. Entropy generation is a very important variables because this gives you measure of irreversibility. Okay, how much irreversible or how much loss due to friction, due to turbulence, due to non-equilibrium conditions. So that is why this parameter is very important to us. And as an engineer, our goal is to decrease the value of this one, because lower the value of this one, you have less loss due to friction, so you have higher efficiency. So that is why the entropy generation value is very, very important to us. Okay, so that's for the closed system. Again, we want to find out in open system, maybe entropy generation. So the open system example could be in compressor, where there is mass in and mass out. So as you know, when you're trying to write the entropy balance equation, when you have entropy in and entropy out, you have entropy due to Q as well as mass. So this is the additional term as compared to the closed system. So these are the additional term: mass in positive, mass out negative, and this one is the entropy transfer due to heat transfer. And this is entropy generation, and this is change in um, entropy of the control volume. So in open system, we call the system as a control volume. You can also write this equation in power form. This one is in total entropy form, and also you can write in specific entropy form as well. If it is steady case, there will be no change in entropy in the control volume, right? Like in the turbine, the fluid is flowing all the time, the property remains same within the control volume, then we call it steady case. So this term would go away, this term would go away if there is no uh, uh, property changing in the system. So this is how you can find entropy generation, rate of entropy generation. And if it's a single stream, instead of doing summation of all inlet and outlet, you just have one um, one inlet and one outlet. And also, if it is steady, if you use the conservation of mass, mass inlet would be equals to mass exit from conservation of mass. That's why you have single mass flow rate here. Okay, and based on what is given in the problem, you can simplify more. If it's adiabatic, again this term would go away. So in the problem, we need to look for whether it's a steady. You can read out whether it's a single inlet or outlet, and also if it is adiabatic. So this is how you can find the entropy generation. So if in open system, if it asks you to find the entropy generation, you can start always with the basic equation and then simplify based on the assumption provided. And you have this entropy, change in entropy, and these values, again remember, entropy is a property, and these value can be obtained uh, by different method. One using the property table, other using a specific heat method. So there are different ways depending on whether it's a liquid incompressible substance or it is a ideal gas. If it gives you gas, you can always consider to be ideal gas and use the formula that are related to ideal gas. So again, if you think about here, it all comes to how you find the value of entropy. Okay, and for finding the value of entropy, there are different ways. Uh, Before that, in the calculation, the most important variable which you need to calculate is entropy generation, and we should know how to calculate the entropy generation for both the closed system and open system. And as we discussed before, for a closed system, if you have a system here, you can consider the surrounding, and you can consider both the system and surrounding within the isolated system, in which Q would be 0, because this is a boundary in isolated system where there is no heat transfer. That's the definition of isolated system. So in that case, entropy generation would be change in entropy of the system plus change in entropy of the surrounding, and this has to be always positive quantity for irreversible process. So, and this should give you a measure of how irreversible the process is. And for open system, as we discussed before, this is the basic equation, and based on assumption on the problem steady flow, this part would go away. Single flow, we don't have the summation, and then steady, and if it is adiabatic, this part would go away. And this is the formula for entropy generation. So depending on what is given in the problem and what assumption we need to use, you can use any of these formula to find the entropy generation for the open system. Again, as I said before, it comes again how you can kind of find the entropy value at inlet, exit, a different state. And the good thing is this is a property. This is a very important thing. This is a property which depends on state function. State function. It is a state function. So if you know pressure and temperature, it is a property. You can find out the entropy. So there are different ways by which you can find the entropy value, and you should know when to use, which to use. depending on the problem. So these are the possible options. I think we already talked about how you can find the change in entropy. I think this is usually used when Q is given like in maybe 30 kilojoule per kg, and if you know the temperature, and this can be used only for a reversible case and when it is a closed system. So you should know when to use this one. So Q must be given, and if the temperature is constant, this is how you find the change in entropy. So this is used when Q is given, temperature is constant, and it is a internally reversible. um, so the other case being if it is a pure substance and if there is change in phase, and if you have a property table change in phase. So for steam, it can change the phase, or the R134A, which is a refrigerant. These property value are given in the property table. So whenever you see this one, always try to make use of the property table to find entropy. Okay, in this case we are looking for entropy. Okay, and for gases, I think for air some of the property values are given, but if it says nitrogen, you may not have the property table. So in that case, uh, if you want to find out change in entropy, again change in entropy, then for instance, if for you can use the constant specific heat method and variable specific method. Constant specific heat method is easier, so if it doesn't say anything, you rather use the constant specific heat method. Okay, so these are the formula. I think we did the derivation, and if you know at 2 point when the process takes place, you are given P1 T1 and then P2 T2. See, this involves, so this use this formula. If the common is temperature, and depending on whether the specific volume or pressure is given, you can use either of these formula. And in each of these there is a special case which we call as isentropic. Isentropic means, again, it becomes isotropic when it is a reversible plus adiabatic. Okay, so if you use this equals to 0, then you can find the relationship between the two state. Like if the process happened, so maybe you have P1 V1 and then P2 V2. So you can find the, if you know any three of these value, you can find the fourth value. So this relation can be used to find the unknown. So this is a very important relationship, but remember, you cannot use this anywhere and everywhere, only for when the process that is taking place is reversible and adiabatic or isentropic. This formula for finding pressure, temperature, especially volume, can only be used when it is isentropic. So like you cannot use for any process, only when it is ideal gas, reversible and adiabatic, and constant specific heat method. If you assume constant specific heat, only then these relation can be used. If it is a variable specific heat, this is the formula to find the change in entropy, and this value also can be found from the table. And then the pressure and the pressure are kind of related using this formula, and these values can be found from the table. So these are also handy when we want to find out the unknown pressure, uh, specific volume, and also the temperature. Okay. um, so again, if you want to find out change in entropy, you can either use uh, property table where there is a change in phase, or you can use a specific heat method for ideal gas. And again, you can use constant specific heat method or variable specific method for ideal gas. And for incompressible substance, if there is no phase change like solid or only liquid, in that case, the formula is, this is the formula which you can use if you know the property, and you can see here it depends just on um, temperature change. Okay, so in incompressible substance, you don't have like Cp and Cv like ideal gas. Cp and Cv are same for incompressible substance. Okay. So this is kind of overall picture. So the type of problem you could be asked from this chapter is, you can be asked to find out change in entropy, just change in entropy. So figure out whether to use the property table whether to use the constant specific method, or if the heat transfer rate and temperature known, you can even use the Q by T, considering it reversible. Okay. So this is an example. This is an example where again all these problems are taken from the problem that we did in the class. These are not the new. Okay, this all everything done in the class. So in this case, like the heat is these are the thermal reservoir, and Q is given and the temperature is constant. So if you want to find out uh, change in entropy, then you better use Q by T. So the possibility is Q by T. So we need to find out which one is more irreversible. So in order to calculate irreversibility, you have to calculate the entropy generation. And if this is a source and this is a closed system, and for that you find the change in entropy of the system plus change in entropy of the surrounding. Do find this entropy generation for the case A and case B and find out which one is more irreversible. Okay, this is one example. This is just, I'm just trying to show like which one to use when and where, depending on what is given in the problem. So another problem where I'll try to show, if it is open system and if you have been asked to find out entropy generation, this value, how you simplify the basic equation to find the entropy generation. And again, it comes to find out, entropy value. Again, remember this is a state function and it is a property. And again, you need to look at the concept map to figure out which one to be used. Okay. So for instance here nitrogen, so you can consider this as an ideal gas. See the assumption is steadily adiabatics, no heat transfer from this pressure to temperature. So P1, T1, P2, T2 is given. Calculate the entropy generation. So in a compressor, this is a open system, and nitrogen you can consider to be ideal gas. You need to find the entropy generation in this case. So open system formula is, you can start with the basic equation. This is the basic equation. It says steadily this part would go away. Adiabatic, there is no entropy transfer, so there is only entropy transfer due to mass, and it is steady, so m1 dot equals to m2 dot from conservation of mass. So this is the entropy generation which we want to find. And if you, we don't know the m dot value, so if you divide by m dot, this becomes entropy generation, which is specific entropy, and it all comes to finding S2 minus S1 between the inlet and outlet. Now which method to be used? So this is ideal gas. The property uh, for finding the entropy is not given in the appendix, so you have to use the specific heat method, and I don't think for nitrogen there is a change in phase. So use that specific heat method. Again, which formula to be used? Pressure, temperature, P1, T1, P2, T2 is given. So the formula that relates this P1, P2, T2, P1, P2, T1, T2. So that is the formula which we need to use. Okay. So our guiding path, like the concept map, is very important to us. The basic equation for the entropy balance is important to us, and you have to navigate through, is it open system or a closed system. Do you use the property table or the specific method? Do you use the constant specific method or the variable specific method? So you need to make a decision at each step and then try to find the solution to the problem. Okay. Next one, sometime you may have to use the property table for finding the change in entropy. So if it is a steam where there is a possibility of change in phase, because the property is there in the steam table, so better make use of the steam table. Or if it is a refrigerant like R134A, in the property table you can find the property. So in that case you tend to make use of the property from the property table that is provided in the appendix. Okay, so here it says water vapor enters at this megapascal and leaves at 100 kilopascal. You have to find with the same specific entropy. So S1 equals to S2. So this is the connecting link between state 1 and state 2, but we don't know like where it lies, right? So we don't know whether it's a superheated vapor, or it's a saturated mixture or subcooled. So if it is steam, there is a possibility of phase change. So better make use of the property table to find the property and find the unknown. So that's an example where you have to use the property table. Okay. Um, Now I'll show you an example where we are using um, specific heat method for incompressible substance. So it could be either liquid and solid. Okay. So this is an example of 50 kg copper block is dropped in insulated tank and contain 90 liters of water vapor. Determine the final equilibrium temperature. So I think the final equilibrium temperature is associated with the first law of thermodynamics. So this is copper is a system here, water is a surrounding. So you can consider both in this type of problem. You can consider this as isolated system. Everything happens within this one. So system plus surrounding is an isolated system, and if you make use of this one, you can find the equilibrium temperature. So the copper is at higher temperature, so it gives heat to water, and water accept the heat. So we need to find out how much is the decrease in entropy for the copper. Copper is a solid incompressible substance, and then water, assuming it does not change phase, that's what we got through the calculation as well. It's not changing the phase. From here you could see that the equilibrium temperature is 16.4, so we assume it's still liquid. um, so now our goal is to find the total entropy change. So that means the total entropy change is change in entropy of the copper plus change in entropy of the water, and we already found the equilibrium temperature. And which method to be used? This is both are incompressible substance. It's not changing phase. I don't think the property for copper is given um, in the property table. So that's the reason why we make use of specific heat method to find the change in entropy. So this one is the formula for the copper incompressible substance, and for water we know the T2 and T1. So this is how you calculate the entropy change for each one of these, and the total entropy change is the entropy generation. So this is like, everything is in, this is like change in entropy of the whole universe. So if you add together, it has to be always positive quantity. So this is like total entropy change is entropy generation, which is positive. So it follows the increase in entropy principle. Okay. um so there may be a problem for some of the gases. It could be nitrogen, hydrogen, helium. So you can, if it doesn't say anything, you can always assume it to be ideal gas. If it is ideal gas, you can always use the ideal gas equation. And you can use constant specific, specific heat method to find the change in entropy. It could be a constant specific heat or variable specific heat method. We should know the formula for that. And this is a special case when it is adiabatic and reversible, or in other words, when it is isentropic. These are the relationship that relate pressure, velocity, and temperature, and this one is for the variable specific heat. Okay. And we did a similar problem. Air is compressed in car engine from this much, reversible adiabatic, which means it is a isentropic. If the compression is this one, determine the final temperature. We are using the variable specific heat. And I think I had this question in the class as well, but we forgot to do using the constant specific heat method. So this is an isentropic case. The entropy remain constant. And for closed system, this is a closed system. And using the variable specific heat method, since the ratio of specific volume is given, you can find out VR2. And this is the procedure which you need to follow to find the temperature. If you know VR2, then if you know VR2, like here, you can VR2 is given here. It lies between these two. If you want to find the temperature, in this case you have to do the interpolation to find the temperature. This is exactly what you did in the class, but I think we forgot to do using the constant specific method. Since this is a isentropic process or reversible and adiabatic, for those, how do you relate uh, the specific volume and temperature. So this is the formula you could see T2 by T1 when entropy is constant V1 by V2. So in this case V1 by V2 is given as 8, and then K is a specific heat ratio, which is Cp by Cv. You can look at the table for air, and then you will find the K is close to 1.4. So this you get from the property table. And T1, again, it has to be always absolute temperature scale, which is 295. The only unknown is T2, which you can calculate from here in Kelvin. So this is handy in this kind of problem. Again, remember this, for ideal gas, this can be used when it has to be ideal gas, it has to be constant in specific heat, and it has to be isentropic. Only when these three conditions are satisfied, only you can use this formula. Okay, very important. So you should know how to calculate different variables, the property, uh, using both the constant specific heat method and variable specific heat method. The other important thing which we discussed is isentropic efficiency, because this is important because whenever the turbine produces work, there will always some uh, energy that is being lost due to friction or some other case, right? So we want to find out for each component what is the efficiency. A thermal efficiency takes into account for the whole cycle, but if you want to find out how is each component doing, right, so we need to calculate what we call as the isentropic efficiency. Like in Rankine cycle, we assume that ideal case isentropic or reversible adiabatic process happens in the turbine, but that is not actually the case. So the thermal efficiency, sorry, the isentropic efficiency is defined by actual turbine work, that means, and then divided by isentropic turbine work, and this work are found from first law of thermodynamics. So you have to make use of the first law of thermodynamics. So you can assume as if like there are two devices, one is actual irreversible and other is ideal. Now we need to find the ratio of these work, and if you use the first law of thermodynamics, if you neglect change in kinetic energy, potential energy, even no heat transfer, then you get everything in terms of enthalpy. So our goal is to find the enthalpy of all these points. So the in case of turbine, it goes from 1 to 2. So this is isentropic, that means ideal case where entropy remain constant. So this is the connecting link between 1 and 2. And for the actual case, again, it is still the same pressure, but the enthalpy is different. Okay, so if you know H1, if you know pressure and temperature, you can find out H1. And then for S2S, the connecting link is S1 equals to S2. So you know S2, and if you know some pressure or temperature, you can find out also S2S. And if you know pressure and temperature at 2A, you can also find out S2A, and as a result of which you can find out the isentropy efficiency. Okay, so if it is 50% isentropy efficiency, that means in the turbine 50% of the energy is lost. That's what it means, right? So uh, that is why this value is important. It is kind of measuring the performance of individual component in a cycle. That is why it's important. Though this is for the turbine, and for the pump it's just opposite. Remember, sorry, compressor or pump, uh, the isentropy efficiency would be just opposite, because in the pump or the compressor we need to supply the energy. Okay, so isentropic case is when you have lowest amount of energy. Okay, and so it's just kind of reverse. So you need to be careful in terms of using the formula for compressor. I think we have done for the nozzle as well. You can find the isentropic efficiency for the nozzle as well. So in the class we did a problem that relates to I think for the turbine. Okay, and you were asked to calculate the isentropic efficiency. So basically we have to know H1 S2A and H1 and S2S, and s 2 s, and you can find the isentropic efficiency. Okay, The other way to put this problem, sometimes the isentropy efficiency is given, let's say 50% or zero point 0.5, and you may be asked to calculate the temperature, or the actual enthalpy, whatever. So it could be one way or other way in terms of asking questions from exam point of view. Okay, so that's all for the review from entropy chapter. So this is a very important chapter.